All right, so we're recording. Welcome back, everybody. I believe this is week 12 of class. I'm starting to lose track of what week it is. But as usual, we have a new homework assignment. This one is going to be due on Thursday of next week because we're starting a whole new unit, and I want to show you some more material in lecture next Tuesday before you have any homework due. Okay? So that's why we're moving that back compared to the normal due date. We also have test corrections. Everyone who's here received their test back, which means you can do the corrections. Just a reminder about how this works. You take your graded test, you look through it. Anything you missed, any problem that you didn't get right, you can redo it. And you'll do that on a separate piece of paper and staple any redo problems to the back of your original test. And then I'll regrade that. And you can earn up to 1/4 of the points that you missed back if you do this. So if you choose to do test corrections, which you don't have to, of course, it's always optional. But if you do choose to do those, that's going to be due on Tuesday. All right? So if you didn't get your test already, I'll give it to you at the end of class. Any questions on that? Okay, so we're going to start this new unit. And just to kind of give you some sense as to where this class is going, what's the end game. We're going to do this chapter on gravity, which is actually coming from chapter 13 of the textbook. So we're going out of sequence for the first time. We're going to jump ahead to chapter 13. And we're not going to do everything in this chapter, because of course there's some stuff in this chapter that depends on material we haven't really looked at yet. Okay? So I'm going to select little bits from chapter 13. Then we're going to do a chapter on momentum, which I believe is chapter 9, and that will be it. So it's just gravity, momentum, and then the course will be over. Okay? We will spend some time towards the end just doing a basic overview of the course. All right? So let's get into it. Let's get into this chapter on gravity. And I'm going to start by giving you sort of a historical perspective. Okay? Now, keep in mind, history is very complicated, and I'm oversimplifying things a lot. I just want to give you an overview of some of the big ideas that were floating around about gravity and how we got from sort of these ancient ideas to a modern understanding of gravity. All right? So let's get to some of those early ideas. So if you go back before what we now call modern science, people had some very different ideas about the way objects out there in space move around. It was commonly understood that the way things move here on Earth and the way things move out there in the heavens, I'm talking about like the planets and the stars, it was thought that those types of motions were very different and that they were governed by like a completely different set of laws. Okay? So there's sort of like one way things work down here. There's a certain laws of physics for motion of earthly bodies. And then there's an entirely separate set of physical laws for heavenly bodies. That was just the common thinking back then. Okay? And to give you a sense of how this looks, a lot of people thought that the motions of the heavenly bodies were quote-unquote perfect, meaning every single planet in our solar system moves in a perfectly circular path, and it always maintains that perfect circular path forever, and it never stops that motion. Whereas motions of earthly bodies were thought to be like imperfect. Okay, so motions that come to a stop because of friction, that was thought of as like an imperfection. Okay? And fundamentally, there was a pretty big understanding that there was a geocentric universe, Earth-centered universe. The thinking was, Earth is at the center of the entire universe, and every single object orbits the Earth. The sun goes around the Earth, and all the different planets go around the Earth. Of course, we know this is wrong, right? The Earth is not the center of the universe, but that was a very commonly accepted idea before modern science. Okay? So this is what we call the geocentric model right here. Earth is at the center, moon goes around the Earth, the sun goes around the Earth, and every single planet goes around the Earth as well as all of the stars. Those also go around the Earth. That was the geocentric model of the universe that was commonly accepted. So now I'm going to tell you why we started to shift away from this geocentric, Earth-centric view of the universe to what we know now, okay? So one of the first kind of indications that the geocentric view of the universe was wrong was something called retrograde motion. Has anyone here ever heard of the term retrograde motion, or that a planet is in retrograde? Okay, here's the basic idea behind that. Let's pick a planet, let's say Mars, and let's watch it as it moves throughout the night sky. So every single night, we're going to look up in the night sky and just say, there's Mars. The next night, we'll identify Mars in the night sky. And we'll sort of just track how it's moving from night to night, okay? What you'll actually notice periodically is that Mars seems to be moving in one direction across the sky, but then it suddenly reverses its direction of motion. It appears to go the other way across the sky, and then back again. That sort of reversal of the motion of a planet across the night sky over many, many days, that's called retrograde motion. And it really makes no sense if Earth is at the center of everything, if you think about it. You'll never see that happen if Earth is at the center of everything and all the planets are just going around us. We'll only see them move in one direction, we'll never see them reverse direction, if that's really what's going on. So we can explain retrograde motion if we don't put Earth at the center of the universe and we just say, well, Earth is just another planet going around the sun just like all the others, okay? So what I'm going to show you is this dot is going to represent the Earth, this dot is going to represent Mars, and we're going to see what it looks like as they both move around the sun, okay? So it's just a little GIF showing you that from our perspective, if we track the motion of Mars throughout the night sky, we'll see its direction apparently reverse over the course of many, many days, as we sort of overtake it in our orbit, okay? So again, the point here is this retrograde motion can't really be explained if your idea is that Earth is at the center of everything, but you can easily explain it if you say Earth is just another planet going around the sun, just like all the others. Okay, so this was one of the kind of cracks in the geocentric model of the universe. All right, so let's skip ahead in time, like several thousand years, and now we're at Nicholas Copernicus, who lived in the 14 and 1500s, okay? So Copernicus was a really big advocate of a heliocentric model of the universe. Heliocentric means the sun is now at the center, and all the planets, including the Earth, are orbiting the sun, okay? And not to say that Copernicus was the first person to ever come up with this idea. People said, hey, maybe Earth's not at the center many, many times before Copernicus. It's just that he was a really big advocate of this, and he was able to convince a lot of people of this. That's the main thing about Copernicus. He was able to actually convince everyone that this was correct, okay? So that's why he's kind of credited with the idea. And of course, if we put the sun at the center and we say Earth is just another planet going around the sun like everything else, we can explain retrograde motion. There's another piece of evidence that came to light around this time period by this guy, Galileo. Galileo was one of the first astronomers to observe the night sky with a telescope. Okay, so not just using the naked eye, but using a telescope. And one thing that Galileo saw was that Jupiter has moons that are going around it. Just like we have a moon that orbits the Earth, Jupiter has moons that are orbiting it. You can't see them with the naked eye, but if you have a telescope, you can see them. And this discovery was huge because, hey, this is an example of some things that are orbiting something other than the Earth, right? So it's obviously not true that everything just goes around the Earth, right? So all of this evidence was building up that Earth is really not at the center, and that a heliocentric model with the sun at the center is much, much more accurate. And when people really started to catch on to this and start taking this as a fact, that was called the Copernican Revolution. Okay, and that's a really big shift in scientific thinking if you think about it. Because it kind of knocks us off our pedestal, right? We're not in some kind of special place. We're not at the center of everything, right? We're just another planet like all these other planets, okay? All right, so this is our heliocentric model. Sun at the center, all planets are going in orbits around the sun. Okay, so let's jump ahead in time a little bit more. There's this guy, Johannes Kepler, who lived in the late 1500s, early 1600s. And what Kepler basically did was took all this new information that was coming to light and really starting to quantify it, right? Really starting to come up with a very mathematically detailed description of how planets move around the sun. And what he did was he studied a huge amount of data that he collected as an astronomer, and he basically tried to find patterns in this data. So what was the data he was looking at? Basically tracking how planets move across the night sky over the course of many, many days, months, and years. Okay, so that's the data in question. He's trying to make some sense of it, trying to find some patterns within that data. And he came up with 3 laws of planetary motion. And we're going to learn about these actually later, like next week. That basically these 3 laws can accurately describe the motion of any planet in the solar system. They describe how Earth is moving around the sun. They describe how Mars is moving around the sun. Basically any planet in the solar system. It's very accurately described by this model. So what Kepler did is he brought this sort of mathematical precision to astronomy, right? We can really quantify things. How far away is a planet orbiting the sun? How long does it take to orbit the sun? We can put numbers to all these things and predict them really accurately. But one thing that Kepler could never do is explain why. He just said, here are some laws that explain how the planets move. What's causing them to move that way? That's what he wasn't able to do. And it wasn't until Isaac Newton came along that we had sort of an explanation as to why planets move the way they do around the sun. And the explanation is gravity. Newton came up with a theory of gravity that explains, why all of these different planets do what we see them do when we watch them move across the night sky. Okay? So that's what the main topic of this lecture is. It's that theory of gravity developed by Isaac Newton. Okay? All right. So let's now get into that. The rest of the time here today, we're going to talk about Newtonian gravity and an equation that Newton came up with called the law of universal gravitation. Okay? So big picture, we have talked about gravity already in this class, haven't we? What do we know about gravity so far?
Goes down.
Goes down, sure. And what is the strength of gravity? So as an acceleration, it's 9.8 meters per second squared. As a force, it's mg, right? But strictly speaking, that only describes gravity at the surface of the Earth, okay? What we're going to do is take a much broader view. How does gravity work in general, not just at the surface of the Earth, but in general, okay? So, has anyone heard this kind of myth about Isaac Newton sitting under an apple tree, then an apple falls on his head, and then that's the moment when he has this great insight and sort of figures out how gravity works? I don't know if that's true. That's probably just a myth. It's a good story, so let's go with it. So the idea is, Newton is sitting there under a tree, just kind of contemplating how the moon orbits the Earth. Why is it that the moon stays in orbit around the Earth? What is it that's keeping it kind of locked to the Earth? And the moment he's thinking about this problem, an apple falls out of the tree and hits him on the head. And the story goes that he realizes at that moment that the force that's pulling the apple down out of the tree is actually the same force that's causing the moon to orbit the Earth. So it's a common phenomenon called gravity. That was the insight. So basically what he showed is that gravity is a force that affects things close to the surface of the Earth, but it also affects those heavenly bodies. We're talking about the planets and the stars out there in space. And it actually works the same exact way down here on Earth as it does out there in the heavenly bodies. Okay? So in other words, the same exact equation can describe how an apple falls out of a tree and why the moon stays in orbit around the Earth. And that might not seem like a big deal right now, but back then that was a huge shift in thinking. Because remember, it was commonly understood back then that the way things work out there in the heavens is fundamentally different than the way they work down here on Earth. And what Newton showed us, no, there's just one common law of gravity that just describes everything. It's universal, okay? That's what we call it. That's why we call it the law of universal gravitation. And by the way, this is an example of something in physics called unification, where we take two things that are going on in the physical world that don't seem related to each other at first glance, but then we show that they're actually the same thing, right? We show that an apple falling is really the same phenomenon as the moon orbiting the Earth. There are other examples of that, unification in physics. For example, electricity and magnetism are really just the same phenomenon. They're two sides of the same coin. That's another example of unification in physics. That's the big goal of physics, by the way. More and more unification. Try to explain more and more things with fewer and fewer theories. Okay? So that's what Newton is doing here. All right, so let me try to convince you of what Newton realized, that the way gravity works here on Earth is the same as it works out there in the heavens, let's say with the moon orbiting the Earth. Okay? So I'm going to show you an animation, and let me explain what's going to go on in this animation. Imagine we have this giant cannon, okay? And it's really tall. Let's say it's so tall that it's just like above the atmosphere, so we don't have to worry about air resistance, okay? And we're going to fire this cannon horizontally. So we'll shoot a cannonball out, and it's going to travel horizontally. We're going to repeat this experiment many, many times. Each time we do it, we're going to increase the speed at which we fire the cannonball. You can probably imagine what's going to happen, right? If we shoot it at a low speed, it'll fall down over here somewhere. If we increase the speed, it'll go a bit further. If we increase the speed, it'll go a bit further. What I want to show you is that if we fire the cannonball at just the right speed, it's never going to hit the Earth. It's going to just end up in orbit around the Earth instead, okay? So here is our original shot. Lands over there in, I don't know, Siberia somewhere. Here's the next one. Lands in, I don't know, the Mediterranean Sea. And here's the next one. That one, since we fired it at just the right rate, it never hit the Earth. Instead, it stayed in orbit around the Earth. So hopefully that's pretty straightforward to picture, right? But what's going on here is that the cannonball is moving so fast, and it is being acted upon by gravity, right? It's not as if there's no gravity. If there were no gravity, it would just go off in a straight line like this. Gravity is acting on it. But gravity is curving it in such a way that it exactly matches the curvature of the Earth in terms of the path it's taking, okay? And if that's the case, you'll never hit the Earth. Instead, you'll be in orbit. You'll be in a circular orbit around the Earth, okay? So you seeing how these things are connected? The same exact gravity that we already know can explain how a circular orbit is happening, okay? And apply this to any object you like. The Earth orbiting the sun, the moon orbiting the Earth. Fundamentally, this is what's happening. Something is moving so fast sideways that it never falls and hits the object it's orbiting, okay? That's really all it is. All right, so I think we get the point, but I'm just going to beat it into the ground one more time. What we imagine is basically a projectile, right? That cannonball that we fire is a projectile. And as we know, with projectiles, they don't just move in a straight line path. Because of gravity, they curve away. So our projectile, we're going to show its straight line path like this. That's the path it would take if there were no gravity. It would just move like this. But then we'll show its actual path in red, like this. And we can see that the red path sort of curves away from the straight line path by some distance d, okay? What we're imagining is the Earth's surface itself is also curving away by the same distance d. And that way you never hit the Earth. All right? So, any questions so far? I know I'm throwing a lot of kind of background information at you. Okay. So, here's what Newton realized, and we're going to get into some formulas now. That if we have an object in circular orbit around the Earth, it's in free fall, technically, just like if you drop an apple, right? Because it's, what do we mean by free fall? Does anyone remember like the definition of being in free fall? It just means that the only force acting is gravity, right? If the only force acting is gravity and nothing else, you're in free fall. That applies to things that are just falling to the ground, like an apple. It also applies to orbiting bodies. But here's the thing, if we're orbiting in a circular path, not only are we in free fall, but since we have this circular motion, the acceleration is v squared divided by r. Okay? So that's all we're going to do here. We're going to sort of combine two ideas, the idea of being in free fall with the idea of being in circular motion. And that's all we need to describe an orbit. Okay? That's all we need. All right, so now I'm going to show you some of the actual calculations that Newton did. He didn't do it exactly the way I'm showing you, but this is the gist of it, okay? So, at the time that Newton was around, people knew a few things about the way the moon orbits the Earth. Okay, so the problem we're focusing on right now is how the moon orbits the Earth. It was known what the period of that orbit was. That was actually easy to measure, right? Does anyone remember what the period of a motion means? What's the definition of period? Yeah, that's how long it takes for one complete revolution. So if we're talking about the period of the moon's orbit, that's how long it takes for the moon to go around the Earth. Does anyone know how long that is in days? For the moon to go around the Earth?
Like 120 something.
It's about a month, actually. A month is pretty, it's more like 27 and change days for the moon to go around the Earth. But it's pretty close to a month, okay? And if you keep track of the lunar cycles, like the phases of the moon, right? The amount of time it takes to go from one full moon to the next full moon, it's about a month, right? And that's the amount of time we're talking about, okay? I'm going to give that to you in seconds, just because we want to be in SI units. But again, this is about a month right here. The period of the moon's orbit is 2.4 10 to the 6 seconds. Okay, another thing that was known at the time was the distance to the moon, okay? I'm going to call the distance between the Earth and the moon little r, okay? So if the Earth's here and the moon is here, that distance is 3.8 times 10 to the 8 meters. Again, this is a number that was measured already and known at the time, okay? Another thing that was known was the radius of the Earth itself. So for that, I'm going to use capital R. That's the typical notation. If you're talking about the radius of some object, use capital R. That was known to be 6.4 times 10 to the 6 meters. Again, back in the day, they didn't measure things in meters, but these are the numbers, okay? So we have all this data, it's well known to us. Now what we can calculate is the speed of the moon's orbit. We can calculate how fast the moon is going as it circles the Earth. It's actually not that hard to do given our data. It's just the distance the moon has to travel in one period divided by the time, right? It's just a distance over time sort of thing. And remember, this is something that came up in the last test. The distance is 2 pi r to go around the circle once. Okay, that's the circumference. And the time is the period t. So here, let's plug in our data. And someone out there, do this calculation for me. 2 pi times the distance between the Earth and the moon, which is 3.8 10 to the 8 meters, divided by 2.4 10 to the 6 seconds. If we calculate that, we'll know how fast the moon is orbiting the Earth in meters per second, right? Yep, so 995 meters per second. It's about a kilometer per second that the moon is moving around the Earth, okay? So that's the speed. How about we calculate next the centripetal acceleration of the moon? Because again, if we're moving in a circle, we know there's a centripetal acceleration. What is the formula for that? Yeah, it's v squared divided by r. We have our v, we have our r. We could calculate the acceleration of the moon as it orbits the Earth just by doing v squared over r. Okay? Pretty simple to do, right? Let's plug in the numbers. We have v is 995 meters per second. Square that value. Divided by r, which is 3.8 10 to the 8 meters. And what does that end up being? It's kind of a small number.
0.0026.
Yeah. So if you work this out, it comes out to 0.0026 meters per second squared. Okay, so a pretty small acceleration as it turns out. And here's what Newton realized, okay? If we're right here on the surface of the Earth, what is our free fall acceleration? If I just drop something and it falls, what is its free fall acceleration? Yeah, so right at the surface of the Earth, acceleration is 9.8 meters per second squared for an object in free fall. But if we're all the way out here where the moon is, this is our acceleration, okay? So what's happening as we get further and further away? Our acceleration is getting smaller and smaller, okay? And what Newton did is basically found a way to describe how that is happening mathematically. All right, so here's what we have so far. The moon accelerates towards the center of the Earth. Remember, it's a centripetal acceleration, so it's going to be going towards the Earth with that acceleration. At 0.0026 meters per second squared. That's what we just found, right? However, if we're at the surface of the Earth, we know that objects accelerate towards the Earth at 9.8 meters per second squared. Let's quickly compare those numbers. Just see how they kind of compare to one another. Let's take the acceleration all the way out here where the moon is divided by g, which is the acceleration when you're right on the surface of the Earth. Someone crunch those numbers for me. Basically take this divided by this, what do you get?
0.3026.
Okay. And yeah, that's what it is in decimal form, but you can verify this. It's about 1 over 3600. It actually, just by a nice coincidence, works out to pretty close to this clean fraction, 1 over 3600. And you, again, verify that. Take this divided by this, take 1 over 3600, pretty much the same, okay? All right. Here's something else we can compare. We can take another kind of ratio. let's take the radius of the Earth itself. That's the distance from the center of the Earth out to the surface, to the distance to the moon, okay? So basically, what are we comparing here? If I'm standing on the surface of the Earth, I'm a certain distance away from the center of the Earth, right? If I'm all the way out here where the moon is, I'm a much bigger distance from the center of the Earth. What's the ratio of these two? Okay, so take this number, 6.4 10 to the 6, divided by this number, 3.8 10 to the 8. And what do we get?
0.0168.
Which, yeah, as a fraction, again, it's a nice coincidence, it works out to about 1 over 60. And then you can verify this in your calculator. Does this suggest anything to you? Just look at these two numbers. Do they relate to each other in some way?
The next exponential.
How many seconds are in a day and an hour?
Yeah. Okay, so yeah, that's another interesting coincidence actually. But what do I get when I take 60 squared?
36 seconds.
Yeah. See, this number is the square of this number. Okay? That's what Einstein realized. So what are we saying? The strength of Earth's gravity gets weaker the further away from the Earth you get. That's what we're seeing. Because it's got a certain strength over here, 9.8 meters per second squared, has a much weaker strength over here, right? The way it gets weaker as you get further away has something to do with the distance, right? Has something to do with your distance. In fact, again, what we're seeing here is if the distance increases by a factor of 60, that's the case if we go from right at the surface of the Earth out to where the moon is, then the strength of gravity decreases by a factor of 60 squared, okay? And that whole idea is the inverse square law. The force of gravity is proportional to 1 divided by the distance squared. This is saying it gets weaker with distance squared, okay? Not just getting weaker with distance, but getting weaker with distance squared. Okay, so any questions on this? So hopefully you're convinced of that. So now I'm going to just give you the full law of universal gravitation. Hopefully you have enough background to be convinced that this is the way it works. So let's just kind of state it in its full form now. The law of universal gravitation. This is what was worked out by Newton. We'll refer to this as LUG for short sometimes. Here's what it says in words, okay? I'll put it to you in words, then we'll put it in an equation. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses, but inversely proportional to the square of their separation. So again, gravity is not just something that the Earth does or that the sun does. Every single particle in the universe, from the smallest thing you can imagine to the most gigantic black hole, exerts gravity, okay? The way it does that is according to this law of universal gravitation. So here's the general picture you should have in mind. Okay, we've got two masses, M1 and M2. These can literally be anything you want. It could be the sun and the earth, it could be the earth and the moon, it could be whatever you like. Just two masses. They attract each other. That's what gravity does. It's an attractive force. So that means M1 is going to be feeling a force towards M2. And at the same token, M2 is going to be feeling a force towards M1. They're attracted to each other. They have a force going towards each other. Okay, R, that's their separation. That's just how far apart the two objects are. And remember, what we've already shown is the further apart two objects are, the weaker the attraction is going to be. The closer they are, the stronger the attraction is going to be. And then of course M1 and M2 are their masses. So here is how we denote the magnitude of the force of gravity between any two objects. It's given by this equation. The force is equal to a number capital G, which I'll explain in a second, times M1 times M2 divided by R squared. Remember, the product of the masses goes on top, the square of the separation goes on the bottom. That's basically what that's saying in words, okay? And then there's some kind of constant out front. This constant is, well, I'll give you the value of it, okay? But I want to just say right off the bat, it's not 9.8 meters per second squared, okay? This is a completely different thing. This is capital G. 9.8 meters per second squared is lowercase g. 9.8 meters per second squared only applies to the way gravity works here on Earth. This is universal. This describes gravity anywhere in the universe. This is far more general, okay? And this constant basically tells you how strong the force of gravity is in general, okay? It's equal to 6.67 times 10 to the minus 11. The units are a little bit weird. Newtons, meters squared per kilogram squared, okay? So the first thing we're going to do on paper today is just try to understand why the units have this, this weird value to them, okay? So here we go. So we have force is equal to this new constant called G, capital G, times M1 times M2, and then divided by R squared. What I want to show you is why G, capital G, has the units it has. So I'm going to solve for it in this equation. I'll multiply through by R squared. So we have FR squared on top over here. I'll divide by M1, M2. So that's on the bottom over here. All right, you guys tell me. What is my SI unit of force, which is F? What do we use for force? Newtons. R is a distance. What's our typical unit of distance? Meters. And we're squaring that, right? And then we have two masses. What is our SI unit of mass? For mass, we're kilograms. We have two factors of it, so we have kilograms squared, okay? So that's where those weird units come from, okay? But what this number G tells us, again, is how strong gravity is, generally speaking, as a force in our universe. If big G has a larger value, all gravitational attraction gets stronger. If it has a smaller value, it gets weaker. It just so happens that in our universe, it takes on this value, 6.67, 10 to the minus 11 newtons meters squared per kilogram squared. And that's not the value here on Earth or here in our solar system. That's the value everywhere in the universe, okay? It's a fundamental constant of our universe. All right, any questions on that? All right, so I'm going to let you try something out. So the claim here is that gravity is universal, right? Obviously, the most important source of gravity for us right now is the force of gravity exerted by the Earth, because the Earth has such a gigantic mass, okay, compared to other objects around you. But it is true that every single object in this room around you is exerting a gravitational pull on you. This stapler right here is exerting a really weak gravitational pull on me. This laser pointer, same deal. It's just that those forces are incredibly, incredibly weak compared to the force of Earth's gravity, okay? So to illustrate that point, I want you to estimate the force between you and the person next to you, the gravitational force between you and the person next to you. What do we need to know? We need to know G. Well, that's the value. I'll just tell you what it is. Then you need to know the two masses in kilograms, right? And then what does R represent again?
It's such a part.
Distance apart. So try to look around the room, look at the closest person next to you, try to just eyeball how far apart you are. Doesn't have to be too accurate. Try to estimate your masses, and then you'll get a force out of this equation. What you're going to see is the force is tiny. Tiny, tiny force. So try it out, see what you get. We're all going to get slightly different numbers because we're estimating different things, but we're all going to be in the same ballpark, okay? If we do this right. So everyone try it out, and then we'll see what the different numbers we come up with are. By the way, who doesn't have their test back yet? I gotta hand these back. Keep your hand up so I can get to everybody. So I think you should have some estimates by now. Anyone want to throw one out there?
Like 3.71 times 10 to the negative 8.
So about 10 to the minus 8. Who else has an estimate?
Something similar to that, where it's 1.0 to the negative 8.
Yeah, about 10 to the negative 8 newtons again. Anybody else get something crazy different? Yeah, we should all be in that ballpark. 10 to the negative 8 newtons. That is not much force at all. It's not even noticeable, okay? That's why we don't notice the force of gravity from everyday objects. We only notice it from incredibly massive objects. The only nearby incredibly massive object is the Earth we're standing on. So that's why we can act as if it's just Earth providing gravity, but in reality, everything has its own gravitational pull, okay? So let me show you the way I came up with my estimate. So everyone's going to have a different mass, but I'm going to take both students to have a mass of about 75 kilograms. So two adults, that's a typical mass, right? And, normally we'd be sitting about 1 meter apart, but social distancing, let's say 2 meters, okay? And now we can calculate the force. That's G, M1, M2 divided by R squared. So we have 6.67, 10 to the minus 11 newtons, meters squared per kilogram squared. That's this constant G. Both masses are 75 kilograms. So 75 kilograms is going to go in twice. Then we're going to divide by 2 meters, which is R, which is being squared. Okay. So if you do my calculation, you're going to get, I ended up getting something like 9, 10 to the minus 8 newtons. And that's kind of the ballpark we're looking at. All right? Any questions on this one? All right, we're going to keep going then. All right, I want to talk a little bit about this number capital G, big G. Because I think it's important to understand what this number means, okay? Capital G is the first example of what we call a universal constant that we've seen in this class. There's some other examples like the speed of light or like the mass of an electron. These are things that are very important numbers in physical equations that don't change as you go from one place to the next, right? These are numbers that just take on the same value everywhere throughout the universe. That's why we call them universal. Obviously, certain things are not universal, right? Like, little g being 9.8 meters per second squared, that's unique to the Earth, right? If you're on another planet, that number would take on a different value. But here we're talking about universal constants that just are the same everywhere. And if we look at it in this equation, right, it's telling us basically how strong gravity is as a force. If you took this number, big G, and you just dialed it up somehow, right, you made it larger, you would make the force of gravity larger. But not just in one place, you would be doing that everywhere in the universe. Every single gravitational attraction would be getting stronger. If you made this number, big G, smaller, you would make the force of gravity everywhere in the universe a little bit weaker, okay? So that's what this number does. It just kind of determines what the strength of gravity in our universe is. We know, because it's been measured, that the value is 6.67 10 to the minus 11 newtons meters squared per kilogram squared. We have no idea why it has that value and not some other value. Nobody knows, okay? It's kind of a mystery. We could easily imagine it took on some other value like 3 million, it could be 0, right? Why does it have this exact value and not something else? Nobody knows. Let me just kind of get you thinking about what it would mean if G had a much larger value or a much smaller value. So what if big G was much, much bigger? That would mean all gravitational forces would be much bigger than they are now. What that would actually mean in our universe is objects would just collapse into black holes, right? So that wouldn't be a good situation. We couldn't be here if that were the case. What if G had a much smaller value and gravity was much weaker? Well, then big structures like the planet we're standing on or the sun or galaxies, those wouldn't be able to be here in the first place. You need gravity to pull things together and form large structures, okay? So it looks like G is right in the sweet spot where structures can form, but they don't just collapse into black holes. So that seems to be the case, but we don't exactly know why. So it's an ongoing mystery. Okay? So I have a quote here from a physicist, Lisa Randall from Harvard. And she's basically talking about how gravity, we might think of it as a kind of a strong force generally, but it's actually pretty weak. So you might find it hard to imagine that gravity is a weak force. But consider that a small magnet can hold up a paperclip, even though the entire Earth is pulling down on it. And just think about that for a minute, right? I wish I had a magnet with me, but I don't. I have a paperclip. But we can easily imagine a magnet just pulls up a paperclip, right? That magnet is basically winning out against the force of gravity. The entire Earth is pulling down on the paperclip. And this tiny little magnet is exerting a stronger force than the entire Earth. That means gravity is pretty weak, right? You need a lot of mass. You need a giant object before gravity becomes even noticeable. That's why we say gravity is kind of a weak force. Okay? All right. I'm going to tell you a little bit about how this number G was measured. So this is called the Cavendish experiment, all right? This was an experiment performed by this guy, Henry Cavendish, in the late 1700s, 1798. And basically, again, the goal of this experiment was to measure this number, big G. which tells us how strong the force of gravity is. Okay, here's the device. There's a lot going on here, so let me just kind of break it down for you. This device is called a torsion balance. What happens on this thing is we have a wire, which is like connected to the ceiling up here somewhere, and attached to that wire is a beam with a mass on either end. So you got a mass here and a mass here. And also on this wire is a mirror, okay? Then on a platform right next to where the wire is hanging, we have two other masses. So this wire can twist, so these masses can move around, but these masses are just fixed, okay? Try to imagine what happens. Gravity is going to attract these masses to each other. It's a pretty weak force, but if we have a really sensitive instrument, we can maybe measure it. What happens if these two things are attracted to each other? The wire is going to twist because they want to get closer together, right? It's going to make the wire twist so that the masses get closer together. When the wire twists, the mirror is going to twist too, because that mirror is connected to this whole rotating beam. So if we basically shine a light at the mirror and then have that go onto a little scale where we can measure where the light's hitting, even if the mirror moves just a tiny little bit, we can notice the light beam moving across the scale. So even tiny little forces can be measured if we do this really carefully, okay? So let's think about it. If I know what all the different masses are, that's like your M1 and M2 in the equation, and I know how far apart they are, that's R in the equation, and I can also measure the force based on how much twisting there is in the wire, then I can calculate G, right? It's the only unknown left in the equation. And so that's why we know that it has the value of 6.67 10 to the minus 11. So this is the same exact experiment. I'm just going to show you an animation of it so it's a little more easy to see. So it's obviously very exaggerated how much things are twisting, but you notice how when the wire twists, when the balls attract each other, it causes this beam to sort of sweep across the scale, like this. We measure the amount of twisting in the wire, we can measure how much force the attracting forces are exerting on each other, okay? All right, so I think for the last little bit of the lecture here, we're just gonna do examples. Not so much talk about the history of this stuff anymore. Just sort of get some practice working with the law of universal gravitation and how to calculate forces with that equation. Okay, that's going to be a big topic in the next homework assignment. So here's our first example. Let's say we have three masses, M1, M2, and M3. Mass 1 is 15 kilograms, mass 2 is 25 kilograms, and mass 3 is also 25 kilograms. Let's say they're arranged in an equilateral triangle, so that the triangle that they form, all sides have the same length. That length is going to be 5 meters. So we have 5 meters going this way, 5 meters going that way, 5 meters going that way. Okay? Question is, find the total gravitational force on M1 due to the other two masses. Okay. So let's think about this real carefully. We're only interested in the forces that are acting on M1. Okay? How does gravity work? It's an attractive force. So, M1 is going to feel a force attracting it towards M2, like this. There's going to be a force going straight down this way, along this line. But it's also going to be attracted to M3. There's going to be another force pulling it along this line. What we're trying to do is find the sum total of those two forces, okay? So, let's do that. Yeah.
Do those forces balance out so that it's always 5 meters between each other?
That's just the way we're setting the problem up, but what you'll see is it's only y components that we're going to be left with. X components are going to cancel if you look at that diagram. So here we have 1 up here, and then we have 2 and 3 down here. Okay, there are 2 forces going on. One of those forces, I'm going to draw it just like this. This is what I'll call F, well, that is not the letter F, F21. That's the force that number 2 down here is exerting on number 1 up here, okay? Then we have this force, which is F31. That's the force that number 3 over here is exerting on number 1 over here. So let's show, using an XY coordinate system, which way these forces are going. So can we see just by looking at this that the X components will cancel out? You see, these 2 forces are equally big. Same masses involved, same distances involved, so same amount of force. But this one's pulling in the positive X direction, and this one's pulling in the negative X direction. So the X components will cancel out. That makes sense? In other words, if I'm trying to find the total force, which is the sum of F21 and F31, the X component of that total force is going to equal 0, okay? I mean, we could work it out mathematically, but hopefully that's just clear to see, okay? That means we only need to think about the Y component, right? So let's get to that. If I want the total Y component, how can I do that? Well, both of these are in the negative Y direction, right? According to the way I set up my coordinates. Let's try to work out what the Y components actually are. So here, for each of these vectors, the Y component is this piece going right here along the Y-axis. We need some kind of angle to work out components, right? Does anyone know, because we have an equilateral triangle, in the triangle itself, what are the different angles we have?
60 degrees?
They're all, yeah, given an equilateral triangle, they're all equal angles, so they have to add up to 180. 60 is what they all have to be, right? But here, I've split that 60-degree angle down the middle. So we have 30 on each side. Does that make sense? Let me zoom in a little bit. I'm running kind of small. Okay, that makes sense? Okay. So somebody tell me, right, let me just kind of copy this down so it's easier to see. If this is the Y component right here, and this is my 30-degree angle right here, what do I use? Sine, cosine? Yeah, I'm going to be using cosine of 30 because this Y component is adjacent to my 30-degree angle. Y'all see that? Adjacent goes with cosine, opposite, which would be over here, that would go with sine, okay? So here's what we have. I have negative, because it's going down, magnitude F21, and then we said cosine 30 degrees will give us the Y component, okay? And then I have negative magnitude F31, and then if I multiply by cosine 30 degrees, I'll get the Y component of this one. So I'm just adding these two downward facing Y components to each other. That's how it's going to go, okay? And by the way, you know, what are these magnitudes? How strong are these forces? That's where the law of universal gravitation is going to come in. So for example, magnitude of F21, That's G, M1, M2 divided by R squared. I'm going to write this as R12. It's the distance between 1 and 2. Make sense how I'm doing the notation? So if I want the force between 1 and 2, that's going to be G times the two masses divided by the distance squared. That's going to be 6.67, 10 to the minus 11 newtons meters squared per kilogram squared. Okay, just have to look back at the problem. M1, that was 15 kilograms. M2, that was 25. The distance between them was 5 meters. Okay, so these were just given values in the problem. If you crunch those numbers, here's what you'll get. 1.0, 10 to the minus 9 newtons. So that's how much force there is between 1 and 2. Okay? But again, we're only taking the y component, so we're going to plug it in and multiply it by cosine later. Okay? All right. What about the force between 3 and 1? Well, that's going to be big G times M1 times M3, because we're talking about the force between 1 and 3, divided by the distance between 1 and 3 squared. Well, 1 has a mass of 15, 3 has a mass of 25 kilograms, so those are the same masses from before. And the distance is 5 meters, just like before. So actually, all of the numbers that go into this calculation are the same as what we already did. So I can just skip ahead and say, that force has a magnitude of 1.0, 10 to the minus 9 newtons. Okay? So we good on that? So therefore, the total force, because again, we see the x components cancel, we're only thinking about the y component, which goes like this. We have minus 1.0, 10 to the minus 9. That was the magnitude of the first force. Then we'll take cosine 30. Then we have minus 1.0, 10 to the minus 9. That was the magnitude of this force. And then we'll take cosine 30. Do that calculation, and what you'll get is minus 1.7, 10 to the minus 9 newtons. So basically, overall, number 1 is being pulled down with a force of 1.7, 10 to the minus 9 newtons. That's what we found. Okay? Any questions on that one? All right, so it's basically, we're just remembering how we add vectors together from way back in the first unit, and then we're just using this for the magnitude of the force vector. Okay? So we'll do one more like this, then we'll take off. So here I have 2 point masses. M1 is over here with a mass of 15 kilograms. M2 is over here with a mass of 25 kilograms. That should say 25 kilograms. Okay, sorry about that. So let's say these two masses are separated by a distance, which I'm calling d, of 4.5 meters. All right, let's say we had a third mass, M3. Question is, where could I put the third mass so that it has zero net force acting on it? So let's think about this, right? If I had a third mass right in the middle, it would be being pulled towards mass 1 like this. It would be attracted to mass 1, of course. But it would also be attracted to mass 2. So it's kind of being pulled in these two different directions. You see that? If there's zero net force, it just means it's being pulled equally hard in both directions. In order for that to work, there's a certain spot we have to put it in such that the forces cancel, right? Like if I put it too close to mass 1, they won't cancel because I have a bigger force pulling it this way. If I put it too close to mass 2, then this force is going to win out. So there's some kind of sweet spot in the middle where the forces cancel out. Okay? So we're going to find that. All right, so I'm going to copy down the picture. we have mass number 1 on the right. We have mass number 3 in the middle. And then we have mass number 2 over here, okay? And what we're interested in is the total force on mass number 3 being 0. So I'm going to show the two forces that act on it. We're going to have F13, that's the force that number 1 is exerting on number 3. We have F23, that's the force that number 2 over here is exerting on number 3 over here. And they're both attractive forces, right? That's the way gravity works. It's always attractive. So if you're ever not sure what the direction should be, just remember it's an attractive force that tells you the direction. Okay. So we have some distances on the diagram. I'm going to label them. This distance right here is what we're calling D. And we're given that distance between 1 and 2. That's 4.5 meters. This distance between 1 and 3, we don't know that. And we're going to call that x to be solved for. Okay, so here we go. If the net force on number 3 is 0, here's what we know. It must be that these two opposing forces have the same magnitude, right? If I'm being pulled to the right with 10 newtons, being pulled to the left with 10 newtons, then they cancel out and give 0, right? So what I'm going to say is the magnitude of F13 is equal to the magnitude of F23. That's how we can get the forces to cancel. Does that make sense? Okay? Let's think in the margin over here about the distances involved. The distance between 1 and 3, that's what we call R13. On our diagram, that's what we're using the variable x to stand in for, okay? We don't know what that is. Okay? The distance between 2 and 3, what would that be? Distance between 2 and 3? In terms of the variables d and x, how would I get this distance? Yeah. See, this distance is the full distance d with this x subtracted off it. Right? If I just want the distance between these two, it's d minus x. That's useful because I'm trying to solve for x, so I want to express all the distances that I don't know in terms of x. Okay? All right, cool. So these two forces have the same magnitude. That means for F13, we have big G, M1, M3 over R13 squared, right? It's the two masses multiplied together divided by the distance squared. For this other force, we have big G, M2, M3 divided by R23 squared. So it's just the force between 2 and 3 here. Notice what I can do. I can cancel out big G, and I can cancel out M3, okay? And I can also do the following. For R13, remember, that's just the distance x in our diagram. So I have M1 divided by x squared on this side of the equation. On the other side, I have M2 divided by, this is the distance d minus x. So I know both masses, M1 and M2. I know the distance d, so the only unknown is x. So we're ready to solve for x. We just have to make sure we, follow the algebra properly. So here's what we're going to do. I'm going to cross multiply d minus x squared to put it on top over here. Then I'm going to divide M1, put it on the bottom over here. So we'll have d minus x over x all squared equals m2 over m1, okay? Everyone cool with how I did that? Okay, so I'm going to do a few things in this next step. I have a square here, so if I square root both sides, I can get rid of the square that's right there. So here's what I'll have. I'll have d divided by x minus 1. See how I can write this as d divided by x minus x divided by x divided by x is just 1. So that's what I'm doing. And I square rooted both sides, so I got rid of the square. So on the other side, I'm going to have square root m2 over m1. But I have to be a little careful. Whenever I square a root, I have to remember there's a positive and potentially a negative root to think about. So I'll just say plus or minus right there, okay? So we're almost ready to do this. I'm going to have d divided by x equals, I'm going to take this negative 1 and just add it so it's over here. 1 plus or minus square root m2 over m1. And then finally to get x, I can multiply on this side to put the x over here, divide by this whole term to put it on the bottom over there. So x is d divided by 1 plus or minus square root m2 over m1. So now we'll just put the numbers in. D is 4.5 meters. And then we have 1 plus or minus the square root. Okay, m2, that was 25 meters, or 25 kilograms, yeah? That was the mass m2. Mass m1 was 15 kilograms. Okay? Punch these numbers into your calculator, you're going to find that if you choose the negative sign, you'll get negative 15.5 meters. If you choose the positive sign, you'll get 1.96 meters. The negative sign is not correct, right? We know that just by looking at the picture, right? We know x is a positive distance, right? It's not like we're over there somewhere, right? So, 1.96 meters is the answer. And what that's telling us is, going back to the picture, if we have these two separated by 4.5 meters, we can put the third mass the distance 1.96 meters away, and it will have zero net force acting on it. But it only works if it's at that very specific distance, okay? So that's going to be it for today. Next time, we're going to talk about circular orbits and calculating things to do with circular orbits.